connectivity with 3 of these samples where we have the interfaces in the reconstruction, and that's where these show up. What you can see is basically, this isn't really an issue, and I'll show later when you have lots of connected particles. It's when you get into structures where you've got a lot of isolated particles, how you define what's connected, what's unknown, and how you treat that starts to give you actual range of error here, and how you identify that. Related to that, so this is actually that same data set. This is the TPV, the active TPV density, electrochemically active. And what we did basically is this is the range that the TPV density could be based on those unknown particles. So we know it's isolated, and we know based on our definition, depending on what our definition is, what's active. But you still have all those unknown particles on the side that could be connected or they could be isolated. And so this basically shows you get higher levels of isolated particles, this range really spreads out. And this just represents kind of a linear average between the 2 extremes. And they're pretty close when you've got a lot of connected particles, but you know, something else you have to deal with is basically deciding what you do with this unknown particle, which is going to be a function of the volume of your reconstruction, your particle size, and a lot of factors, structural factors. This is just what I highlighted earlier. So this is the same study but the YSE phase, which was you know, everything above 90% connected. You can see for all these different connectivity methods, there really wasn't much variation. So it's not an issue when you've got nicely connected structures. It's only when you get these high isolated particles. So I'll kind of go quickly. I've got like 4 minutes left, or 3 minutes.
We have 9 minutes until questions on this.
Okay. So this is how we do our TPV calculation. So when you deal with a voxelized structure, we're identifying the TPV segments as these edge lengths, orthogonal edge lengths of these cubic voxels or rectangular, depending on what the dimensions are. But the problem with that is if you measure any sort of line in 3D space, continuous line, and you're only doing it by orthogonal segments, you're going to overestimate the length of the line. And how much you overestimate is a function of the direction that the line is pointing in this voxelized structure. So just 2 examples, you know, if your line happens to be on a plane going at a 45-degree angle, we know the correction is √2. You know, we're actually measuring, you know, the sum of these 2 lines is √2 greater than the direct length here. If you're going on the edge of a cube, or from corner to corner of a cube, it's √3. So sort of thinking about this, the idea was, well, what is the average correction factor for a network of TPVs that in theory are going in every single direction randomly and isotropically? And so what we did was we sort of solved this analytically, where we just integrated this orthogonal line length, which is just x plus y plus z, and divided by this direct length, which is x squared plus y squared plus z squared. And then we integrate this over the entire sphere of all possible angles that this line could be going. That's actually easier to solve, and you can solve it directly if you convert to polar coordinates, and it looks kind of messy. But this is the solution it gives, which is that in general you're overestimating the TPV line length by this 1.455 factor. And we did a similar analysis. Peter did, instead of just the 2 spheres, we actually obtained these artificial structures from Craig Metcalf at the University of Toronto, who does structural modeling, where he put a bunch of spheres together into a structure. It's 100 particles, and we basically know everything that we want in the structure, and we know the exact TPV length because it's solved by the sphere radii, and it's going to have a circle of this specific TPV length. And that's what we're showing here. So this line represents the actual TPV density of this structure. And again, we did voxels per particle diameter, so we changed the resolution of this structure. So we basically cut it into slices and voxelized it. And this was the TPV density just adding up those line lengths that I talked about, the orthogonal segments. And you can see it evens out as you increase your resolution. Now if we introduce this factor, this isn't a fit, this is just what we derived and then we're applying it to this. You see that it actually matches this quite well. So we're seeing that as long as you have, and at least for this structure, which is only 100 particles, which actually isn't that big, that past a certain resolution, in this case, it looks like it's maybe 15 voxels per particle diameter, that this actually fits the TPV density quite well. So that was nice to see that sort of this theoretical, mathematical idea actually fit kind of experimental results. Our tortuosity we calculate based on a finite differences method, where we take the pore structure or whatever structure could be YSC, solve the steady state diffusion equation. There's also this geometrical shortest path method that we got some introduction to. And there's someone at Northwestern who's done this, and we've compared values, and they're pretty close, but this is sort of ongoing. We'd like to really do a full comparison. We can do surface curvature analyses where we're studying the radii of curvature, and you can plot these as called ISD plots or kappa-kappa plots, where the type of curvature, so whether you've got kind of a closed sphere, concave or convex, or saddle structures, and you can see changes in these general curvature of the structures depending on your composition. Now, two things I wanted to mention. Okay, so one, interface identification I think is really interesting and is challenging, especially with YSC electrodes, composite electrodes. Basically, where is the interface here? How do you identify that? And lastly, multi-scale structures. So this is a top-down view where you've got these kind of big particles, but then within the particles, it's really fine scale porosity. And how do you treat that going forward? And this actually applies a lot to, we're starting to do some lithium-ion battery electrode work. You've got large particles with very fine cracks, fine surface, and how do you treat those? Okay, thank you.
Okay, we have a few minutes for some questions. I had one small question. I was quite happy to see you puzzling over the effect of the FIB-on effect.
Yeah.
But I've also been thinking about that for quite some time.
Yeah.
You were at high accelerating voltages?
That was 30 kV, yeah.
Electron.
Oh,
Yeah.
electron? No, that was anywhere from 2 to 5 kV. I think it might have been 5 kV for that. But yeah, it's higher than the really low.
Because when we were looking at it, it was around 15 kV in the SEM, I think.
Okay.
Yeah, I puzzled over the mechanism behind this. The other thing I could come up with was something like surface charging effects.
It's interesting. I don't have some of the pictures here, but we also try this on the FEI instrument. And you also get a mechanism where you can get, if you do the low accelerating voltage, like 1 kV or 2 kV, you can pull out the nickel YSC contrast, but then if you turn the ion beam on, what you hadn't seen was actually isolated nickel. And then you image the isolated nickel when the ion beam is on. So it's almost like it's some surface issue that is independent of the conductivity of the phase.
So that would be actually cancelling out your percolation issue that we quite often do, where that nickel particle would be charging positively.
Yeah. Okay.
Have any more questions?
Sorry, I'm not in this field, but just to give me an idea. I mean, it seems you've advanced quite a lot in terms of the organization. How long does it take for you to do one of these 10 by 10 by 10 micron reconstructions and the full suite of data analysis after that?
In theory, if you drove from the microscope to your computer, if sort of some of those later images where they're really nice and you don't have to do any sort of hand analysis or hand fixing of the images, you could do it in a day. Generally, the image collection takes about 4 hours just to mill out the area and then automatically mill through. But once the programs are written, it's just a matter of the time it takes to save all the images, and then you might want to rename them, and then you have to do all of these procedures, kind of shoving the sets of images from one step to the next. But the steps themselves are, the threshold